What Dave Farina showed is that amino acids polymerize in water, not in a hydrophobic pocket. Even in the hydrophobic pocket that Bruce has, he's not doing amino acid coupling, no way, because they would never go in his hydrophobic pocket if they were Zvid or ionic. It wouldn't go in there.
Hi, I'm Steve Meyer of the Discovery Institute. I'm going to be hosting an occasional podcast, which we are calling The Story of Everything, from the Big Bang to the Origin of Life and Beyond. And today we have our second interview with Dr. James Tour of Rice University, an organic synthetic chemist and nanotechnology engineer. James, as many of you know, has taken on the debate about the origin of life, and that has resulted in a whole series of videos back and forth. And Jim, I wonder if you could just start by telling us, giving our audience a little context as to how this debate started and where we are in the debate now and who the main players are.
Okay, I gave a talk for the Discovery Institute about 3 years ago in Dallas, and that got a YouTuber, Dave Farina, really upset, and he came out with a video on origin of life. He had about 1 million subscribers, so he's quite a large presence on YouTube. And he said that I was all wrong in my analysis. So I came out with a 13-part series where I go through the chemistry of the origin of life. You can find that on my YouTube channel, Dr. James Tour, or there's a link below, just below this video, to that series. And then after I came out with that series, Dave Farina came out with a 2-part series where he was saying that my 13-part series was all wrong. And so now I have another series coming out responding to his 2-part series. And his 2-part series, he finally brought on some experts. Now I can critique the experts' work. And so this, to me, is a real advantage, because now, rather than going after a YouTuber, I can really address synthetic chemists that he brought on and show their own chemistry, that it screams out, this is not how life could have happened.
Excellent. So Dave is not himself a PhD scientist or chemist, but he decided to take you on because of the consensus view in the textbooks or something, I suppose. And then you responded by giving a rather thorough 13-part exposition about what we know about chemistry and how it relates to the origin of life. It's an excellent teaching series. And then he attacked you again, I would say rather foolishly, but our audience can make that determination for themselves. And so, but this time he brought in some actual chemists. So you're not going to, in responding to him, you're not going to have to punch below your weight class, as it were. And you can respond to colleagues in the field and have a spirited scientific discussion about this really important issue of the origin of life.
That is correct. And the first person he brought on was Lee Cronin, which you and I dealt with in a former video, and we talked about his chemistry. And today we can begin to speak about Bruce
your
Lipshutz.
Friend and colleague, Bruce Lipshutz. Now, before we get into the specifics of what Professor Dave, or Dave Farina, he calls himself a professor, I guess, but Professor Dave has said about Lipschutz's work, let's just first talk a little bit about why the origin of life is such an important topic, both scientifically and even philosophically.
So many people like to talk about evolution and how higher organisms came up from lower organisms. But before any of this could have begun, we had to get that first life, that first cell from which other cells came forth, and then evolutionarily a diversification, it is said, that then goes to these higher life forms. At the base of all of this is that generation of the first living cell. Origin of life deals with this first living cell. This is something fundamental. And the whole thing about life is it's very hard to define. We can define its characteristics. That's not hard to define. But to define exactly what it is, what is that spark that occurs that brings life to a cell? What is that spark? It's something that's even hard to define. And you probably can explain this better than I can, because you are a philosopher.
Well, I did my PhD on origin of life biology in a philosophy of science department, and one of the figures that I studied extensively was Alexander Oparin, who was a Russian biochemist who wrote some of the first kind of comprehensive books trying to make a case for what's called chemical evolutionary theory. And as you put it very nicely, there's two branches of evolutionary theory. There's biological evolution, which attempts to explain the origin of the first living, or the origin of new forms of life from simpler pre-existing forms. And then there's chemical evolutionary theory, which is the attempt to explain the origin of the first life from simpler non-living chemicals. And Oparin was really the pioneer in chemical evolutionary theory. He had a very helpful quote. He said that the question of the nature of life and the question and the problem of its origin have become inseparable. And they're inseparable because what we know about how life functions today, what its characteristics are, what its features are, defines the target of what we're trying to explain. And I think anyone who formulates a plausible theory of the origin of life must explain the origin of life as we know it, not some hypothetical entity that might have some analogous features to a living system, but life as we know it. And as we've discussed in previous conversations, life, though it's hard to define in its entirety, we do know a lot about the features of life as we know it. And we know there are four basic chemical compounds that are part of living systems. And I wonder if you could just review for our audience what those are, because that does form part of the target. You've got to explain, at the very least, the constituent molecules out of which life has been formed.
Okay, so you have to have the lipids, which form the bilayer, the structure around the outside of the cell. Those are the lipids, and they have a polar head group. They have a head group that dissolve in water and a nonpolar tail. And the nonpolar tails stick in toward each other, and the polar head groups stick toward the water that's on the inside and the outside of the cell. That's the first class. The next is the amino acids. There are 20 amino acids. 19 of them are chiral, meaning that they have a non-superimposable mirror image. And you have to have all of those in order for there to be life. And then you have to be able to make the polymers of those. And it's the ordering of those in the chain that decide what that particular protein is going to do. Is it going to act as an enzyme that is going to carry out certain functions? Is it going to act as some other structure within the cell? And then you go to the sugars, or sometimes called carbohydrates, sometimes called saccharides, and the polymers thereof. The sugars are a very difficult class of compounds to make. We think sugar is simple. Sugar is a very difficult molecule to make, and they all have multiple stereogenic centers, meaning centers from which chirality emanates. And then you have the nucleic acids like the RNA and the DNA. And the way the nucleic acids are made is you have to take a sugar ribose, or a modification of a sugar ribose called deoxyribose, put on a nucleobase onto that, and put a phosphate, and that's called a nucleotide. And as those polymerize, then you get the RNA or the DNA. And according to the nucleobase that's on there, it defines the letter, and then 3 letters define a word, and that word is what's translated into a particular amino acid that's going to be built. And these become the polypeptide chains for the enzymes that are nature's little nanomachines that build us.
That's an excellent summary, Jim. Let's, if you don't mind, let's break that down with each of those 4 classes just a little bit more, so we make this as accessible as possible for people who don't have a background in organic chemistry. If we think about, let's start with the DNA. You use the analogy of a letter and a word. Many people know from their basic high school chemistry that DNA, a nucleic acid, has a beautiful double helix structure, and that structure was first elucidated by Watson and Crick in 1953 in a famous article that they wrote after a period of intense research. And what some people don't, I think, appreciate is the information-bearing properties of DNA, just how really important that is. In 1958, Francis Crick first formulated what he called the sequence hypothesis, where he realized that those bases that you were talking about are functioning, as you say, like alphabetic characters in a written language, or like we might say today, the digital characters in a section of machine code, which is to say it's not the physical properties of the bases that attach to those to that sugar phosphate backbone that matter, but rather it's the arrangement of those bases in accord with an independent symbol convention that we now call the genetic code. So those molecules, building those molecules is difficult, but getting the sequential arrangement of the constituent parts of the molecules so that they actually carry information and convey instructions for building those proteins, that's another level of complexity altogether that has to be appreciated. So that's a comment on that. Let me make a comment on your the lipids that form the cell membrane. Many people think of those as quite simple, but you and I both have a colleague, Tony Fuderman, who's a lipid biochemist, and he's emphasized that the lipid membrane is anything but simple. And one thing that I remember learning about in cell biology was the gated channels through which molecules pass back and forth, and that the cell carefully controls what goes in and what goes out. And there's a gradient, an ion gradient there that's involved in that. So we might think of the membrane as the simplest part of the origin of life problem, but that's turning out to be very complicated as well. You've mentioned the sugar molecules are difficult to build, and this point about chirality. Can you tell us a little bit more about that? I think, is it the case that all four of these classes of molecules are built by homochiral constituents?
That is correct. Yeah.
And the analogy that was used to explain this to me first was the idea that you think of a mirror image. You've got a left hand and a right hand, that all these molecules have structures that have mirror images. And for reasons that we're only recently beginning to understand, each of the four classes of molecules that occur in life are homochiral, meaning they only have one-handed a one-handed version of the molecules. With amino acids, only left-handed amino acids. With sugars, only right-handed structures. And this is a mystery that has to be explained when we explain the origin of life. And as I understand it, we're nowhere near to explaining this origin of the homochiral structures of these four classes of molecules. Is that correct?
That is absolutely correct. And so what people have made in laboratories in any system where they say it's prebiotically relevant, including the Miller-Urey reaction, they've always made the mixtures, the left-handed and the right-handed, if you will. And those could never be used. It's more recent work by people like Ron Naumann that have shown in a new phenomenon called chiral-induced spin selectivity that biological systems had to have had near complete homochirality for all of their molecules at the start. It's not something that could have been evolved into. So this puts another layer of complexity upon the already super complex task of trying to see how you could build a cell.
So when you're trying to simulate any one of these four classes of molecules by starting with simpler compounds and allowing them to react one with another, you have to simulate a process that is life relevant. Somehow you have to produce only left-handed amino acids, only right-handed sugars, etc. You can't get a mixture. If you have even one right-handed amino acid, you will not form a functioning protein. So there's a problem of specificity here that has not really been addressed by these prebiotic simulation experiments.
That is right.
Correct?
Yeah. When you say one, you mean that instead of having, say, L-aspartic acid, you had the right-handed if
you got one right-handed amino acid mixed in with in a chain of left-handed amino acids, then that's going to mess up the folding of that chain, and you won't get a functional protein.
That is correct. If you just had one in a particular chain, it depends on where it is. Generally, what you have in a biological system is you have something that will fix that, or something that'll take that thing out or not use it. But if you had, for example, just instead of having one of them one type of them, the other enantiomer, And by type, I mean that all of the ones are in there. You're going to have many of those in a chain, and it generally will not work. You have to have all of them being homochiral. You can't have
Okay.
mixtures on any of them in order for that to work. That's correct.
Especially in the protein active sites, for example.
Yeah,
That would be critical not
That'd be
to
critical.
mix in.
Right.
Yeah, okay. All right, so that's excellent. So let's now move on to the whole question of the of amino acids and which form proteins, because I know that's what a lot of what Bruce Lipshutz's work on Origin of Life is concerned. And we've all learned about the prebiotic soup or the warm little pond, or that was Darwin's phrase in a letter he wrote to a friend, Joseph Hooker, when he was speculating about the origin of life, but also acknowledging that neither he nor anyone else had any really well-developed ideas about where the first life would have come from. But he used the idea that, well, he imagined that there might be all sorts of the right kind of compounds dissolved in a warm little pond, and now we've advanced to the idea of a prebiotic soup. There's something kind of curious about that I think very few people recognize, and that is if you want to build a polymer, you want to link together amino acids to form a peptide chain in hopes that you get the right sequence of amino acids that will actually fold in the right way to perform a protein function. The first thing you have to do is polymerize those amino acids. You got to link them together. But few people realize that amino acids will not polymerize in an aqueous environment, in a warm little pond or in a prebiotic soup, that water has a quenching effect on the polymerization reaction. First, I'm going to check that with that perception with you. You're the chemist. Is that correct? And then how have people tried to circumvent that problem when they're doing origin of life simulation experiments?
That's correct. They don't polymerize in water. So what Lee Cronin does is we talked about this last time, is he dries them out. He gets rid of the water because the reaction has a positive free energy, meaning that it's not going to go in water. And that's taking into account these two thermodynamic properties, enthalpy and entropy at a particular temperature, make up the free energy. And the free energy equation tells us that this is not going to proceed. So what Bruce Lipshutz does is he drives the amino acids into a hydrophobic pocket. And now there's no water around, and he gets these things to couple. But it's a totally loaded system because the amino acids are extremely water soluble, because all amino acids exist in what's called a zwitterionic state, meaning that they have a plus charge and a minus charge on them simultaneously. And because of that, they're highly polar molecules, so they dissolve in water. And so how does Bruce Lipshutz get them to go into a hydrophobic pocket? Is he will get rid of that zwitterionic charge by either wrapping up the amine group on one component, and then he'll wrap up the carboxylic acid on the other component. And so he no longer has a free amino acid. He has done something synthetically in a laboratory to it that would never happen in nature.
And this, again, as we've discussed in previous conversations, is the general methodological and even philosophical problem with many prebiotic simulation experiments. In fact, I would say all prebiotic simulation experiments. They purport to simulate what would happen on the early Earth as a result of undirected chemical processes, but instead to get life to move in a life-relevant direction, or to get chemicals to move in a life-relevant direction, the synthetic chemist himself or herself must engineer the system, must direct the system, must exert their own influence and guidance on it. And we have another example of this in trying to get a very seemingly basic thing to happen, which is to get the amino acids to link up to form peptide chains that might end up performing protein functions.
Right. And then the other thing that Bruce Lipshutz had is he had totally unnatural activating agents to get the amine to couple with the carboxylic acid. So he didn't have amino acids. He didn't have zwitterionic structures. He had to functionalize them so that now they will become hydrophobic and move into the hydrophobic pocket. So again, quite unnatural, something that doesn't happen on early Earth. Then even when it's in there, they don't hook up. You had to have activators. In order to get a carboxylic acid to couple to an amine, you have to do an activation. So he had an unnatural activator in there. So he didn't make a polypeptide linkage. He didn't make peptide linkages because these were totally loaded systems. And the last thing that was interesting about what Lipshutz did is that so about half of the amino acids just have the carboxylic acid on one end and the amine on the other. But the other half of the carboxylic acids have an extra functional group that's there. There's an extra functional group that's hanging off between the carboxylic acid and the amine, and that ends up interrupting the normal polymer chain because this extra functional group will compete with this amine or compete with this
to form linkages.
Right, to form linkages which are totally unnatural. And so this never happens in ribosomal synthesis because the ribosomes are functioning off of biological enzymes and they're very selective. But in a laboratory, prebiotic earth, these don't exist. In a laboratory that's simulating prebiotic earth, these shouldn't exist. In prebiotic earth, they didn't exist. And so these always compete. So what Bruce Lipshutz did is he only used the amino acids that don't have. So he only used the half. So he only took the ones that don't have it. So it was totally loaded because he didn't have this ionic structure. He put on a big hydrophobic group on either end that would drive it into the lipid bilayer, into the hydrophobic pocket. He used unnatural activators, and he only used the ones that don't have those competing structures. It was loaded at every step.
And if he had used amino acids that had those competing structures or allowed for then you would end up forming linkages at odd angles off of the peptide chains you were trying to build. Is that the problem? That
is the problem, and that's a real problem for synthesis. It's like trying to build words with upside down letters and letters coming off at instead of words across, you have letters coming down vertically, and you wouldn't know how to read that word.
And so those sorts of chains with things coming off at odd angles are not going to fold into the specific three-dimensional structures that will allow a peptide chain to perform a protein function.
That is correct.
So, and what about these activators, Jim? What did he use to activate these connections such as they occurred?
He used totally unnatural activators because usually if you have an amine and a carboxylic acid, the carboxylic acid will take the amine will take the proton from the carboxylic acid, so you get what's called a salt, and that salt is unreactive at anything near room temperature. The only way you get those reactions to form is you have to heat them up to like 130 degrees, what Lee Cronin did. And to make nylons, you heat them up to temperatures that are over 200 degrees centigrade. So you can use chemical activators that will allow this to form so that the carboxylic acid reacts with an activator, the amine reacts with the activator, and it'll hook these two together. These are totally human-designed systems, and that's...
Oh, I see. There's sort of mediators of the reaction, then, that you have to insert into the reaction in a way that is unnatural to what would have been going on in the prebiotic earth.
Right, and that's what Bruce Lipshutz uses. Now to Dave Farina's credit, he did mention that there are unnatural activators in there. But what he didn't mention, because he didn't have the ability, because he didn't notice it, is he didn't mention that there were no Zwitter ionic amino acids like they would be in their native form. They had big hydrophobic groups put on them to drive them into that pocket. And he didn't mention that Bruce Lipshutz didn't use any of the amino acids, of which about half of them exist, half of the amino acids that had that extra side chain that could compete. So again, it was a totally loaded system.
And tell me about the creation of the side pocket. It sounds like there must have been some design involved in creating that little, the hydrophobic pocket, rather.
Right. So the other thing that Bruce Lipshutz used is he used designer surfactants. He called them designer surfactants. He designed the surfactant to get these molecules to go into that hydrophobic pocket. They're not naturally occurring hydrophobic moieties. And you have to be really careful on how you design hydrophobic moieties, because if you just have pure oil, they'll phase separate. But here you have to have a little bit of a polar function to get these to disperse properly in the water. So these are, as Bruce Lipshutz put them, designer surfactants. So Even the surfactants, even the hydrophobic pocket that he put it in was unnatural. It's loaded at every step.
Right.
And,
right.
But Dave never really noticed that.
Yes, and well, you know what I think about this, that in my work studying the methodology of origin of life simulation experiments, these experiments are based on the logic, the uniformitarian logic that is used in all historical sciences, that the present is the key to the past, meaning our present knowledge of cause and effect should guide our understanding and our assessment of the plausibility of scenarios about what might have happened in the past. So if you do a simulation experiment, you need to carefully look at what's all the factors, all the causal factors that are involved in producing the simulation or producing the outcome of that simulation. And if invariably you have to have designer surfactants or interfering, you have to, the investigator needs to interfere to prevent cross reactions, or if you have to choose certain reagents that are purified in a laboratory, which involve an intelligent agent, invariably, I think what is going on is that what's being simulated is the need for intelligent agency to move simple chemicals in a life-friendly direction. And the prebiotic simulation experimenters seem utterly blind to the role of their own hand, their own mind, in achieving the results that they get, such as they are. Because, as you point out, they're not generating life itself. They're not getting anywhere near that. But even the modest movement they get towards life seems to be intelligently designed at each step of the way. And even their vocabulary will sometimes reveal that. Ribozyme engineers, as they're called, or designer surfactants. Very curious.
Yes, it is curious. And this has been pointed out. People would say, Tour, why don't you write articles for the primary literature that expose this? Because they've already been written. As you've said, James Shapiro wrote a whole book on this, you mentioned last time.
Robert Shapiro.
Robert Shapiro wrote a whole book on
two fantastic
this.
scientists, one a cell biologist, but the other an origin of life chemist.
Yes.
Robert Shapiro.
And then also Reichert, Clement Reichert has written an article that was in Nature Communications, a good journal, where he talked about this whole interference problem, where you have to be able to have reactions that have minimal investigator input, and you'd have to be able to use reactions that have a lot of impurities around, because that's the only thing you'd have on early Earth. You don't have ways to purify compounds. So he's put it out there. Well, why don't people then heed to this? They don't. They ignore it. This is the real reason why we have to now go on a social media platform. One of the things is to hit the masses of people. Dave Farina has now over 2 million. He used to have 1 million. Now he has over 2 million subscribers. And so how do you get this word out? It's not by writing primary literature articles anymore. I know how to do this. I've written a few primary literature articles in my life. I know how to get
over 600 at last count, I think. So, yeah, I think it's absolutely correct. And by spotlighting this in the context, in a media context, it is sort of calling people out and forcing people to address the problems. Because as long as the research community is a closed community of people who hold all the same assumptions, that life had to have arisen by a completely undirected materialistic process, and all we're doing is elucidating some plausible ways by which that might have happened, they fail to be self-critical. And I think the field has needed external accounting, and I think you're providing that. And before you, Robert Shapiro used to do that. And I think many people in the field, when pressed, will acknowledge, as Lee Cronin did with you recently, that they don't actually know how you get from how they get from
small molecules,
simple small molecules that are non-living to anything life relevant, let alone life itself. But that's not the impression that the public is getting through standard biology textbooks or videos or museum presentations. And so I don't think you need to apologize for doing something in the social media. I think this is a long overdue accounting for this field.
Right, and I'm only doing what the reviewers of their own papers should have done.
Should be doing.
Reviewers should have stopped it. So these are obviously getting reviewed by others in the origin of life community, And so it's sort of an incestual sort of review that you're getting those that are working in this same sort of community to review each other, because anybody who's working from outside the community would see this and say, this is not relevant to prebiotic chemistry.
And Jim, I want to highlight that word should in your last statement, because the reviewers really should be calling these things out, because there are well-established methodological protocols in this field. This is what I did my PhD on, studying these simulation experiments and the methods that are used in the historical sciences. And if your claim is that you are simulating something that could have and might have and would probably have happened on the early Earth, then you need to make sure that the starting chemicals and conditions that you select match what we know geochemically about the early Earth, number one. And number two, if your claim is that these things happen by an undirected process rather than by a designed process, you better make sure that design that intelligent design in the form of the simulator himself or herself, the chemist, is not playing a crucial causal role in the outcome of the experiment. And I think your critique is showing that both of those methodological criteria are not being met, that the early Earth conditions, the conditions in the experiments do not match conditions that would have been present on the early Earth, and there is obviously a huge amount of direction coming from the intelligent chemist in producing what modest outcomes are being presented in these experiments, or being produced in these experiments.
That's true. Everything you said is correct, and it's been presented in the primary literature, but these folks that work in the area of origin of life are ignoring it. So I'm just putting the word out there on a social media platform, and since now 3 experts have come on to Dave Farina's channel, I'm going right after them in the same medium.
And Dave himself has challenged you on a number of factual things. For example, in this discussion of Bruce Lipshutz's work, he has said, Dave Farina has said that that amino acids will polymerize in an aqueous environment, in water, but but that clearly can't be true, because Lipshutz goes to great lengths to create a hydrophobic pocket in which to try to get polymerization to take place. So his own experiment seems to presuppose that polymerization is not going to take place in water. Am I missing something, or is that right too?
So what happens is Dave Farina read the title that Bruce Lipshutz wrote. The title was forming peptide bonds in water. That was the title. But titles are not...
Of the paper.
The title of the paper is not really that descriptive of what he really did. Remember, what he really did is he never had an amino acid. There was never a zwitter ionic structure. It was not done in water. It was done in a hydrophobic pocket. He had to have big groups put on there that were totally synthetic to drive it into the pocket. He had to have activators that would never be available on an early Earth. And then he had to use designer surfactants for them to move into these hydrophobic pockets. But just in the title, you keep titles short. So he says peptide formation, peptide bond formation in water. So Dave reads the title and calls me a liar because he says it's right there in the title. The title says peptide formation in water. So it says that, so I must be wrong, because he did not have the ability to read the paper.
To actually understand the details of the paper,
right,
what it really showed, and what it presupposed,
right,
which is that you can't form amino acids in water.
Right.
Or you can't polymerize amino acids in water. But now you have a long relationship with Bruce Lipshutz, and he's acknowledged some of these same points to you. So tell us about that interaction and how it relates to what was presented by Dave Farina in his video.
Okay, so what Dave Farina did in his video, he said that Bruce Lipshutz was responding to my 13-part series where I was talking in the particular section about peptide synthesis, that Bruce Lipshutz was responding to my video. Well, Bruce had made a video, he sent it to Dave, and Dave put it in there as if he had been responding to my video series. So when I saw that, I contacted Bruce. When I saw what Bruce had in Dave Farina's video, I contacted him. I said, what was wrong with what I said on my video? You didn't really specifically say anything that was wrong. What did I say that was wrong? Because I've known Bruce Lipshutz for almost 40 years. That's a long time. I don't know how old Dave Farina is, but he might not even be 40 years old. So I've known Bruce a long time. And he says, what are you talking about? I said, you appeared in a video by Dave Farina. You were commenting on my video saying I had it wrong, that it's no problem to make peptide bonds in water. What did I say was wrong? And I sent him the link to Dave's video. And he says, the link that you sent me is news to me. I never approved any of it. He wrote that to me in an email, and I disclosed that email in my video. Publicly. I disclose it. I put sections of it in the video, but the entire email chain, the entire thing is in the link just below that video in the description box. You can link to that and you can read the entire PDF except for like 3 sentences where Dave Farina is talking about, where Bruce Lipshutz is talking about how he knows Dave Farina and members of his family and things like this that I thought were a little bit personal. I didn't want to reveal anything about Dave Farina and his family, so I excised that out. But other than that, those few little sentences, there's like 5 pages of email transmission between Bruce Lipshutz and myself, where Bruce Lipshutz ends up, first of all, saying that he didn't even know that Dave was putting this in there as a comment to me. He was only commenting on his own work. And he watched my video. He didn't see anything wrong with my video. And he ends up in his email, he writes how he agrees with me. Peptides don't form in water. Not going to happen.
Which is presupposed in the experimental protocol that he sets up to try to get them to form in a hydrophobic, that is non-water environment, right?
And not just hydrophobic, but a designer surfactant with designer coupling agents with knocking them out of the zwitterionic structure by putting hydrophobic groups on there with no side branches on them, which half of the natural amino acids would have. So 7 points.
So in a sense, Lipshutz is actually showing how difficult it is to make life in a prebiotic environment, or how difficult it is just to polymerize amino acids in a
just to make a dimer, just to make a dimer, just to make a dipeptide.
Which is two amino acids.
Not the 200 that you need to have an enzyme.
Yeah.
And so this is what he's saying, and he says in his own emails. He says, first of all, Farina put this in there, and I never approved any of this. Second of all, I wasn't responding to you. Third of all, we both know, he writes in there, we both know this is not going to happen in water. So I'm like, why don't you teach this to your friend? Teach it to him, because he thinks it happens in water. And then he finally admits, yeah, if I had used ones that had the active side chains, it couldn't work. So every point that I've made, he confirms in his own messaging to me.
So a fellow organic chemist has confirmed the very same points that you've made about the chemistry, and in essence about why a realistic prebiotic environment would not be capable of generating the polymerization reaction that's necessary to form protein.
That's exactly the case. And what it shows...
In a sense, I'm wondering, is what Lipshutz is doing, is he sort of experimenting to see, well, what would be necessary to get this reaction to take place, this polymerization to take place? But when you get to the end of all the manipulations that have to be made to make that, the question is, well, what is the moral of that story? Is it that prebiotic that prebiotic chemistry will naturally move easily towards a life-friendly direction, or is it the opposite? Is it that prebiotic chemistry will not move naturally in a life-friendly direction, given all the manipulations that have to be made to get even 2 amino acids to link together?
Right, and again, remember, he wasn't hooking together amino acids. He was hooking together just a carboxylic acid and an amine, not amino acids, zwitterionic structures. But to Bruce's credit, Bruce is just trying to show that he's trying to develop techniques, synthetic techniques, for doing organic chemistry in water. Organic chemistry in water is really hard. That's the way nature does it.
Was he making any claims about origin of life, or only peripherally?
Only peripherally. Poor Bruce he thought that if I refer this to origin of life, that it's going to have origin of life. He doesn't know anything about origin of life chemistry. He is really just trying to teach organic chemistry techniques and show how we can get them to go in water, which is very important for the field, because we have to move away from fossil fuel type chemistry, solvents, and be able to do organic chemistry in water without using organic solvents, large amounts of organic solvents. So to his credit, he's helping with that. But then he makes this reference very tangentially to how it might have something to do with origin of life.
Relevance.
But he doesn't even really know the field, and he stepped into a landmine. He stepped on a landmine. The poor guy stepped on a landmine, and he stepped on a second landmine by sending this video to his friend when his friend asked him, Dave Farina, not knowing that Dave was going to insert it as...
Use it polemically in a debate with you.
Exactly. Yeah. And so that was an underhanded thing by Dave Farina to have stuck that thing in there. Now, Dave came out with another video saying, that Lipshutz knew about this all the time, but I've got emails from Lipshutz saying, this is new to me. I never proved any of this. He had not seen my series. He was not commenting on my series, and he had hoped that it would. And he had told Dave, "Don't ever use it in any way that is going to be conflicting with me." And he says it has been used in exactly the way he had told him not to use it. That's the whole problem with this.
Jim, it was also used to try to besmirch your reputation and your qualifications and your knowledge. And turns out it's rather obvious from the standpoint of anyone who knows any organic chemistry that you can't polymerize amino acids in an aqueous environment. That's a well-known fact. And Professor Dave is just simply incorrect about that. And your new video summarizes a little bit of the back and forth about this issue and the actual status of origin of life research in light of what Lipshutz has shown, which I think is pretty obviously showing that the problem is even harder than we thought. And so I think you've done a great service by getting this information out there. And to our audience, we would just commend this new video that Jim is putting out about this question of how amino acids could be polymerized, and the debate that's taken place between himself and Dave Farina, and the way in which Bruce Lipshutz was unfortunately enlisted to play a role in that debate. Now it appears apparently against his own wishes.
Conscription.
So, he was conscripted. Yes, exactly. So anyway, our purpose here is to highlight this interesting discussion that's going on the internet, and in the process to get more clarity on what chemistry has actually shown about the origin of life. And we are very grateful to Jim for spending some time with us again today. And we'll be highlighting his new video about this episode in the discussion. And we'll have an article about it on Evolution News. There'll be a link in that article to this video and also to Jim's video. And so we again want to thank you for spending time with us.
In the description box just below, you'll see the link to the YouTube video that we're talking about and to my YouTube channel, Dr. James Tour. So you can go there and see all these videos that are coming out and see how these experts came on Dave Farina's channel, and they end up agreeing with me over and over again. They end up agreeing with me. And poor Dave Farina, the victim, he never realized any of this. So it's just kind of a sad state of affairs for the young man.
Well, I think you have done a great job highlighting the actual state of play in origin of life research, and I think people will learn a lot of science if they dive into this question and watch your new video. So thank you very much again for spending time with us today.
My complaint to Dave was that he showed a picture of amino acids, and I'll say it again, amino acids that are zwitterionic in their native state in water, polymerizing into polypeptides.